The write-ahead log, referred to throughout this manual as WAL, is a sequential file-based subsystem responsible for durability guarantees in transactional environments. The WAL operates independently of the main data store and maintains a strict depend-only insertion pattern. All modifications to the database state must be written to the log prior to application to the primary storage structures. This ordering constraint ensures that in the event of system failure, the log can be replayed to recover committed state. Log entries are structured as fixed-width records containing a transaction identifier, operation type code, and payload data. Each record begins with an 8-byte header containing the record length and a CRC32 checksum. The operation type field occupies 2 bytes and defines whether the entry represents a write, delete, commit, or rollback action. Payload data follows immediately after the header and varies in length depending on the operation class. The WAL maintains an internal sequence number counter incremented with each record insertion. This counter persists in a fixed memory mapped region and survives process restarts. The file descriptor for the active log segment remains open throughout the system lifecycle unless an explicit segment rotation occurs. Writing to the log involves advancing the file offset and issuing a synchronous write system call followed by an fsync invocation to guarantee kernel buffer flush. Log segments are rotated when the current file exceeds a configurable maximum size threshold, typically set to 64 megabytes. Rotation involves closing the current segment, creating a new file with an incremented sequence number suffix, and updating the active segment pointer in the metadata region. The segment rotation mechanism does not block incoming write requests. Instead, pending writes queue internally until the rotation completes. Previous segments become immutable and eligible for archival. Transaction coordination uses a 2-phase commit protocol. The first phase, preparation, requires all affected log entries to be written and flushed to stable storage. The second phase, commitment, involves writing a single commit marker containing the transaction identifier and a timestamp. Rollback operations insert a rollback marker referencing the transaction identifier, invalidating all prior entries belonging to that transaction during recovery processing. Recovery processing occurs during system initialization and reads log segments sequentially from the oldest available segment forward. The recovery algorithm maintains an in-memory transaction table tracking all active transactions. For each entry encountered, the algorithm either adds the transaction to the active table or marks it as completed. Entries belonging to incomplete transactions are discarded during the forward pass. The recovery process is blocking and must complete before accepting new requests. The WAL supports both synchronous and asynchronous write modes through a configuration parameter. Synchronous mode issues an fsync call after each record insertion and waits for the system call to return. Asynchronous mode batches multiple records before flushing to storage. Asynchronous mode provides higher throughput, but introduces a window where committed transactions may be lost if the system fails before the next scheduled flush interval. Segment archival moves completed segments to secondary storage after a retention policy interval expires. The retention policy is defined as a minimum number of completed segments to retain in the primary storage location. Archival is performed asynchronously and does not block normal log operations. Archived segments remain accessible for point-in-time recovery queries but are typically stored in slower, higher-capacity storage systems. The WAL metadata region occupies the first 4096 bytes of the log file and contains the current segment number, active transaction count, and last known recovery checkpoint. This region is updated atomically using a compare and swap operation to prevent corruption during concurrent updates. The metadata persists across segment rotations through a shared mapping file independent of individual segment files. Compression of log entries is optional and controlled by a configuration flag. When enabled, individual record payloads are compressed using the LZ4 algorithm. The compression context is maintained per transaction to preserve locality. Compressed records include a compression flag in the header and the uncompressed length field. Decompression occurs during recovery processing and returns the original record format to the transaction application layer. The WAL exposes a set of configuration parameters adjustable at startup time. The segment size parameter controls when rotation occurs and ranges from 16 to 256 megabytes. The flush interval parameter specifies the maximum delay between write completion and storage flush in asynchronous mode and ranges from 1 to 1000 milliseconds. The retention count parameter sets the minimum number of completed segments to retain. All parameters are read from a configuration file and cached in memory. Monitoring metrics are exported through a metrics collection interface. The interface exposes the current active segment number, total records written since startup, cumulative bytes flushed to storage, and current recovery processing time during initialization. These metrics are sampled at regular intervals and available to external monitoring systems. No metrics are maintained in persistent storage. All counters reset on system restart. Error handling in the WAL follows a fail-safe model. If a write operation encounters an I/O error, the error is returned to the caller and the transaction is automatically rolled back. If metadata corruption is detected during recovery, the recovery process halts and reports the corruption offset to the operator. No automatic recovery from corruption is attempted. The system remains in a read-only state until the operator resolves the corruption manually. The WAL integrates with the buffer pool through a write-back callback mechanism. When buffer pages are evicted from the pool, the buffer manager invokes the WAL callback to flush any pending log entries associated with those pages. This ensures log entries always reach stable storage before their corresponding data pages. The callback is synchronous and blocks eviction until the WAL flush completes successfully. Performance tuning for the WAL involves balancing durability guarantees against throughput requirements. Increasing the flush interval in asynchronous mode improves throughput, but increases the window for potential data loss. Increasing the segment size reduces rotation overhead but increases recovery time. Compression reduces storage I/O but increases CPU utilization during writes. Trade-offs should be evaluated based on application workload characteristics. The write-ahead log operates invisibly to application code and requires no explicit management. The log automatically persists all transactional state and recovers transparently on system restart. The configuration parameters should be tuned based on durability requirements and hardware characteristics. Under normal operation, the WAL maintains system consistency and enables reliable recovery from any failure point in the transaction lifecycle.